Alright, in today's video, I'm going to be going over three-phase transformers. So we have two types. We have the three single-phase transformer and the three-phase transformer. So I'll go over here to show you. This one is the three single-phase transformer. As you can see, we have three individual single-phase transformers connected to a three-phase bank. And then on the right side here, we have a three-phase transformer, which is just one transformer, and you have three phases sharing a common core. Alright, so for the three single-phase transformer, they're most commonly used by the supply authority. They're harder to connect, larger, higher cost, simpler in construction, and cost less for a spare. So this is because, let's say if one transformer breaks down, you can just buy one single-phase transformer to replace it, which is cheaper than buying a whole three-phase transformer. For the three-phase transformer, it's most commonly used for distribution, easier to connect, smaller, and lower cost. They have a more complex construction, which is why it'll be more expensive to replace the whole thing if this breaks down. Single-phase transformers are much simpler in construction. These are also harder to connect because you're connecting three individual transformers together. Okay, so for the CSA phase displacement requirement, there's going to have to be a 0-degree phase displacement between the high and low voltage side for a Y to Y and delta to delta. And for a Y to delta and delta to Y, there has to be a 30-degree phase displacement between the high and low voltage side. So I'll just go over this explanation. So if we have a Y to Y, we come into line A, and line A is going to be connected to neutral, which is in the middle here. So A to neutral. And then if we go on to the low voltage side, it's going to be the same thing. So we come into line A, and then line A is going to be connected to neutral. And then same for delta to delta, we come into line A, and for a delta, your neutral is going to be in the middle, so A is going to go to neutral, that. And then you go to the low voltage side, come into A, line A, and then to neutral. Is going to be exactly the same as the high and low voltage side, so they don't have any phase displacement. And then now if we go on to a Y delta, we're going to go to line A and then to neutral. Okay, and if we go on the low voltage side, same thing. I'm going to come into line A and then to neutral, which is in the middle. And as you can see here, they're going to be at different angles. Each phase is going to be at different angles. So that means that there's a phase displacement. Because let's see, this is going to be, let's say this is 0 degrees. This is going to be leading the low voltage side by 30 degrees, right? And this is going to be at 0 degrees, right? So that's going to be at 0, and this is going to be leading the low voltage side by 30 degrees. And then we go on to a delta Y, same thing. We're going to come into line A, and then to neutral, and then line A to neutral. Okay, so if we look at the high voltage side, it's going to be 30 degrees from 0. And then low voltage side, it's going to be at 0 degrees. So A to neutral is going to be at 0 degrees on the low voltage side, and A to neutral is going to be at 30 degrees on the high voltage side. So that means the high voltage side will lead the low voltage side by 30 degrees. So now going on to the CSA standard for connections. They have a set rule for how you should connector transformer just to make sure that you won't blow it up or short it out. So for pretty much all other connections other than the delta to Y, it'll be the same. The rule is H1 and X1 must be connected on the same line. So the high voltage side on X1 and low voltage side H1 and X1, they have to be on the same line. So if we go into an example here, this is a Y to Y right here. And if we look at H1, that's going to be connected to line A. And then X1 here, that's going to be connected on line A as well. And then for the next one, same thing. It's going to be H1 to B, so then that means X1 has to be connected to line B as well. Okay. Now onto the special connection rule for delta to Y. H4 and X4 have to be connected on the same line. That can also be H2 and X2, depending on if it's a dual winding transformer. So if we go down here for delta to Y, it's going to be a special connection. So it's saying that H4 will be connected to line B, therefore X4 has to be connected on line B as well. All right, so pretty simple. Yeah. All right, so now I'm gonna go over some simple transformer calculation questions. So here we got a line voltage of 72 kilovolts, and we need a secondary line voltage of 600 volts. All right, so we can't do a delta connection because and a delta line and phase voltage are the same. So if our line is 72 kilovolts, our phase voltage will also be 72 kilovolts, but our transformer isn't rated for that many volts. So we're gonna actually have to do this connection in a Y because phase voltage reduces line voltage by √3. So we just have to divide that by √3 and we actually get this number right here. So that means we're gonna have to connect it in Y. And we're gonna have to do this in series to connect the windings in series because each winding is gonna be 20 kilovolts. And if we connect it in series like I did right here, the phase voltage is gonna be 41 kilovolts because each winding will add up. So each winding is this much, right? And they will add up in series because voltage adds up in series. So that means our total phase voltage is going to be 40 kilovolts, right? And if we do it in parallel, like this, our line voltage will be same as our winding, our windings rated voltage, because that's just how it works in parallel. The voltage will be the same in parallel. Okay, so now on to the secondary side. We want secondary line voltage of 600 volts. But we can't do this in delta either because if we do it in delta, our phase voltage also has to be 600 volts. But that won't work because it's not rated for that much. So if we actually divide this by √3, if we did this in a Y connection, our phase voltage will be 347 because it's line voltage reduced by √3 and it gives us 347. And this is also the high voltage setting for the windings. So that means it'll have to be connected in series like I did here. It's connected in series as well. So that's how you connect it. And then you have to abide by the CSA standard for connections. So now we know that this is a Y to Y transformer connection. H1 here has to be connected to line A, and that means that X1 also has to be connected to line A, and same for the others. Alright, now for the calculation, it's pretty simple. Pretty much the only thing actually there's not really anything different. So first of all, we gotta find the transformer's total rated kVA. So each of these is going to be rated 150 kVA. Each single phase transformer, like it said up here, 150 kVA each. And for the total kVA this three-phase transformer puts out is basically just add them all up. So 150 kVA times 3 and gives us 450. So that's its total kVA it can output. Now we can just go over here. Primary line voltage, already said here, it's going to be 72 kilovolts. Our phase voltage is going to be what we selected here. So we connect it in series, so we're going to get a phase voltage of 41 kilovolts, and each coil will be rated 20 kilovolts. Secondary side, line voltage is going to be 600 volts. Since we connected it in Y, it'll be root 3 less, which is 347. So our phase voltage is 347. Each coil is going to be 173. All right, now for our max rated current, yeah, it's pretty much the same thing in how you would calculate current for three-phase electrical systems. Nothing really different. So you basically get your kVA, and then it's root 3 times your line voltage. For phase voltage, it's your total kVA, and then root 3 times your phase voltage here. So it's basically you just drag this here and drag this here. It's pretty simple, and then total kVA on top. It's root 3 here because you use root 3 for line values and 3 for phase values. And of course your coil, each coil will have, so each coil here will have 3.6 amps because this is connected in series, and when it's connected in series, your current always stays the same. And it'll be same thing for the secondary side. Now for your line-to-line ratio here, what this is talking about is the ratio between the high voltage line side and the secondary line side. So the ratio here is basically just this voltage divided by this voltage. Your primary line voltage divided by your secondary line voltage. And that gives you your line-to-line ratio. Here, so it's basically 120 to 1. And your transformer ratio is basically talking about your winding ratio. So it's the ratio between the phase. It can also be the ratio between the phase voltage here and the phase voltage here. And that's your transformer ratio. It should also be called your turns ratio. So you take your phase voltage and divide it by the phase voltage on the low voltage side, and it'll be 120 to 1. Alright, so now I'm going to go over this delta to Y transformer calculation question. So another thing to note, this is a delta to Y. So I'm going to use this special connection rule for the delta to Y transformer. So I have H4 here connected to B. That means I must connect X4 to B, line B as well. And then for the next one, H4 to C, X4 to C. Last one, H4 to A. That means X4 has to be connected to A. Okay, so now we have, it says we have a line voltage of 2400 volts and a secondary line voltage of 208 volts. Now, if we look at the primary side, here are our dual winding settings. So each winding is going to be 2400 volts. And if we connect it in series, we'll get 480 in parallel, 2400 volts. We want to connect it in parallel because 2400 volts matches our line voltage. That means we can connect it in parallel in a delta connection, because in delta, line and phase voltage stay the same. They're equal to each other. And to connect it in delta, we just go line A here, connect one side to A, one side to B, and then B to C, and C to A again. So it's a closed loop. It's like A, B, B, C, C, A, and then back again, right? Just how it would be like that. Closed loop. Alright, now we go on the secondary side. We have 208 volts we need. And here are our windings, dual winding setting here. It's going to be 120 volts and 240. We're going to use 120 because if we do 120 times root 3, that gives us 208. And it's going to be connected in delta, right? Alright, not delta, Y, because if we connect it in Y, 120 times root 3 equals 208, which we'll get here. So since this is the low voltage setting, it'll be parallel. So these are both going to be in parallel to give us the low voltage setting. So yeah, there we go. And then we go to for here, we're going to have our voltages. So yeah, we have 2400 volts for our line. Since this is a delta, our phase will also be the same. So it's going to be the same voltage. Our coil is also going to be the same because it's in parallel. Just fix that there. And then secondary, our line voltage will be 208. It says right here. We connect to this in Y, so our phase voltage will be root 3 less. So divide that by root 3 and we get 120. And since this is in parallel, our coil is also going to be 120. Or yeah, the coil is always going to be 120. It doesn't matter if it's in parallel or series. Yeah, so we have our current. So to find our current, we have to find our transformer kVA for each of them. So these are going to be each 15 kVA, and then we just multiply it by 3 to get the total kVA of the three-phase transformer. And like we did last time, we just do 45 kVA over root 3 times 2400 volts, and we get 10.83 amps. We use root 3 when finding line values, and then go down here, 45 kVA over 3 times 2400 volts. Use 3 when finding phase values. You get 6.25 amps. Our coil will be half of this of our phase voltage, because when we're connecting in parallel, the current coming in will split up. So that'll be half of our phase current. So each coil will be getting half of the phase current, which is 3.25 amps. 1.25 amps, yeah. So now secondary side, same story. Do the same thing here, and then that'll be half of that. Alright, line to line ratio is basically the same thing as we did last time. We take our line on the primary and line on the secondary and divide them by each other to get the ratio between them. So that's 5:1. Transformer ratio is the turn, also known as turns ratio. We take our phase voltage and divide them, and we get the transformers ratio. Right? Now we can go on to this question right here. So it's saying if this transformer bank supplies a three-phase 24 kilowatt load with 80% lagging power factor, what is the current drawn? So we're looking for what current the transformer would draw if we added this load to it. So it would be like connected, I don't know, it would be like connected like this, I guess. It doesn't really matter what type of load, it could be a Y or delta load. It'd be connected to that bank. So first of all, we have to find the kVA. So it'll be, we'd do the triangle, 80% power factor, it's a 24 kilowatt load. So what we can do is pretty easy. We just find kVA by dividing 24 kilowatts divided by the power factor, and then we get 30 kVA here. 30 kVA. So now we basically found our total kVA of the load, and it'll be pretty much the same thing as we did here, except the max kVA is 30 kVA because that's the max kVA of the load we're supplying. So it's the same thing, except we just replace this with 30 kVA. And same thing, here are our current values. So this is what the this is what the transformer draws when we when it supplies a 24 kilowatt load with 80% lagging power factor. Right. Also, I forgot to go over how to connect. I explained how to connect your transformers in Delta. I'll go over the Y connection. So for a Y connection, it's a little bit easier. So like we did here, we have H4, X4 on the same line. So we got that right. And then for the Y, pretty much our X1 will go to neutral. So basically they'll go to neutral. Right? So another thing to note, might be confusing like how you decide to connect this, whether like you have to connect your windings in parallel or series. And if you need if you have to have it in Y or delta. So just the rule you can use is like if your line voltage is equal to the same as any one of these, you connect it in delta, and then whichever one it is. So this one, the smaller number, will be in parallel, so you select that. But if this was like, let's say 4800 volts, oh, you would just use the high voltage setting, so it would be in series, so you connect it in series, and delta because they're the same, right? But then for the low voltage side, 208 doesn't match up with any of these numbers, so we know it has to be in Y. So we use Y, and then we use this lower number because what is root 3? 120 times root 3 equals 208, right? And then that's why we know we have to connect it for 120, which is the low voltage setting, which will be in parallel. So that's just one rule you can use if it confuses you of like how you should do it. Yeah.